Our second example problem for day 11 is really a lot of the same. We're going to be looking at a roller coaster or a minecart, the classic energy problem. And we have a very squeaky pen here. I apologize for that. But we have our roller coaster happening at a bunch of different locations. And basically what this is allowing us to do is our previous question, we only could really deal with, we were able to show how we could deal with this either with our kinematics or we could deal with it with our energy equations. Because it was just dropping straight from the air, we knew all of the equations, we could deal with it that way previously already. This is one we couldn't deal with already. So what we have is initially our roller coaster is up a total of 80 meters into the air. Do I have a mass for this roller coaster? 735 kilograms. It goes down its bottom piece and hits a point where our height is equal to 0 meters. We're at the bottom of this hill. It then goes up a little bit of a jump to a point where we have a height of 60 meters. And it drops down, well, these guys are in line, may not look like it, to a height of 0 meters. But it hits a frictional pad. We'll put little sparks coming out of the end of it here. Hits a little frictional pad and velocity goes to 0. So it actually is stopped by this frictional pad or hitting the brakes of our roller coaster here. So we have our woo roller coaster ride going on. Okay, for this, I'm going to go ahead and label each of my conditions. So I've got state 1, state 2, state 3, and state 4. And then I am going to go ahead and look at what I'm after. So what to find? So let's throw them. I think I want to throw my work underneath, so I'm going to try throwing them up here. So what to find? I would like to know my potential energy. I'm not going to write it all out this time, so PE at state 1. I would like to know my velocity after the first drop, so that's velocity, so velocity at times 2. I would like to know my velocity at time 3. So when I get to the top of this little hill, velocity 3. And I would like to know work by the brakes, because the brakes are an outside force, so I want W. It's really W happening at 4, but really you've got a 0, a 4.1, 4.2 that work is happening. The brakes are stopping it between two locations. It moves while it's stopping. Okay, let's start. Potential energy, and I've got a nice little spot down here for it. Potential energy at 1 is equal to mass times gravity times my height at 1. My mass is going to be 735 kilograms. Gravitational constant is 9.81 meters per second squared. And my height is 80 meters. I multiply all of those things together, and I get a potential energy at 1 of 576,828 joules. And that is my potential energy at 1. Easy enough. Let's move to state 2, and I now want the velocity. Well, to get velocity, that is related to my kinetic energy, so I'm going to look at my energy between 1 and 2. So potential energy at 1 plus kinetic energy at 1 plus work between 0 and 1 is going to be equal to my potential energy at 2 plus my kinetic energy at 2. Ooh, right in the middle of my face there. Potential energy at 1, I have as 576,828 joules. Kinetic energy at 1, I have a velocity at 1 of 0. Work between 0 and 1, I'm not told about any outside work going on. I'm not worried about friction. I've got a frictionless track in this question. So that is equal to potential energy at 2 plus kinetic energy at 2. If I wanted to calculate my potential energy at 2, mass times gravity times height at 2, well, height 2 is 0. Anything multiplied by 0 is 0. So I've got my kinetic energy at 2. I wasn't asking for kinetic energy, though. I was asking for velocity at 2. Kinetic energy is equal to 1/2 mass times velocity squared. So I can say that my velocity is going to be equal to the square root of 2 times my kinetic energy, 576,828 joules, divided by my mass, which was 735 kilograms. I'm still on the board. And that gives me a velocity of 39.62 meters per second. And that is me velocity at 2. Got away from that pen before it died, thankfully. Now let's look at state 3. So I lose face space on the board. So in this case, I'm going to, again, start with my energy equation. I can use 1 for the start, or I can use 2 for the start. I will go ahead and use 2 for the start. So I have potential energy at 2 plus, oh, I'm off the board. Potential energy at 2 plus kinetic energy at 2 plus work between 2 and 3 is equal to potential energy at 3 plus kinetic energy at 3. I'm off the board. This guy isn't quite level, it looks like. We're going to be slightly off the board here just for the sake of moving along. Potential energy at 3 plus kinetic energy. That's too far off the board. This angle is going to bug me. Kinetic energy at 3. Oh, and I've got the dot there. Okay. Potential energy at 2 is 0. Kinetic energy at 2. Kinetic energy at 2 is 576,826 joules. Work between 2 and 3. We're not told about any friction or anything that's happening between 2 and 3, so that must be 0. Potential energy at 3. This guy I'm going to have to drop down because this little black square is a little white square, but I cannot record that area of the camera for some reason. So potential energy at 3 is going to be mgh at 3, while height at 3 is going to be 60 meters, so this is 735 kilograms times 9.81 meters per second squared times 60 meters plus kinetic energy at 3. I can multiply all this together and subtract it from the left side to get a kinetic energy at time 3. And that value comes out to 144,207 joules. And then with that value, I can find my velocity. And I'm going to do it over here because I'm going to be standing in the other hole that I have for myself. Kinetic energy at 3 is equal to 1/2 mass times velocity at 3 squared. Kinetic energy at 3 is 144,207 is equal to 1/2 times 735 times V3 squared. I get a value for V3 of 19.81 meters per second. Velocity 3 is taken care of. Okay. Those 3 are the easy 3. And I'm going to give myself a little space here so my face isn't all over the board, covered in words. This guy right here. I want work done by this piece. So for this, I can actually just use my long equation and just solve for whatever the work is in order to get this condition to happen. And that is the work that happens between those. I can choose any step along the way. Now, for most of these, when we've had these examples, I've been choosing the step right before it. That's the safest because it makes sure that I'm not, oh, there was actually work here and I forgot about it. In this case, if I do the step right before it, I know exactly if there's work there. If there's no work between it, we could grab from any location. We could go 1 to 4, 2 to 4, 3 to 4, no problem. Even if there was work, we could do that. We just have to incorporate that work. The reason I'm not going to choose 3 is because I have both a potential energy and a kinetic energy at state 3. So I am going to go ahead and I can choose 1 or 2. It won't make a difference. I'll just go ahead and choose state 1. But I can say potential energy at 1 plus kinetic energy at 1 plus work between 1 and 4 is equal to my potential energy at 4 plus my kinetic energy at 4. Okay, I have already worked with 1, and I know that I have no kinetic energy there. I do have a potential energy, and I do know that that potential energy is 576,828 joules. Work between 1 and 4 is the work that's happening right here because we don't have any other work happening. So I called that work 4 in parentheses before. We'll keep with the same naming convention. Potential energy at 4, I'm at height of 0. mgh, if h is 0, it's going to come out to 0. Kinetic energy at 4, I've got a velocity of 0, 1/2 mv squared. If velocity is 0, that's going to be 0. There we go. So my work done by this brakes, I'm going to call it work brakes, is going to be equal to negative 576,828 joules. Meaning that I've been labeling this work 1 to 4 as work in. If I've got negative, work done. So I've got negative, we're losing energy. The brakes are pulling 576,828 joules of energy out of my system. So, well, in class we'll talk about work and naming work conventions at some point, but we're not there yet, so I'm not going to worry about it. It's all based off the thermodynamics anyways. With that, that is our example problem 2. Take care.